My name is Adrian. I'm from Guatemala. Currently, I'm part of the Google Developer Expert Program, and I'm here to talk a little bit about machine learning APIs and Android. The title, it's reference to Lewis Carroll's book, and you'll find several quotes during the talk. We're going to cover a few things here. There are a lot of slides, and all the slides are and will be available on this short link. So keep in mind that at some point, I'm showing samples or code and might be going too fast for you. Everything is going to be available for you to check it out afterwards. So we're going to cover a couple of different parts during this talk. At first, I will show a little bit of samples, several things that are built using machine learning. Then we're going to cover some theory about machine learning, neural networks, and how does this even work. And finally, we'll review some samples using several machine learning APIs. As the title mentioned, we're focusing only on computer vision. There are two things that are like in a current state of the art. That's computer vision and NLP. During this talk, I will focus only on computer vision, but mention a few things about NLP. And so that's the agenda for this talk. So machine learning, it's a trendy topic. It's we've been hearing this about this here and there, even at the keynote at the Google I/O. The Google CEO mentioned that now they are a company that's AI first. So it's important for us as developers and as people working in tech to understand what machine learning means, what impact it's going to have on our work, and how all these buzzwords relate to each other. I mean, machine learning, deep learning, AI. So first and foremost, as an introduction and to set context, I would like to mention that there are several problem sets in computer science that maybe for us it's easy to understand if it's something simple or complex to implement, but might not be as simple to explain that to people that it's related to tech but not exactly developing. So keep this in mind. One of my main goals with this talk, and I've been doing this talk in several conferences, and speaking about machine learning is trying to demystify the topic and make it easy and approachable for everyone. So we'll start with a few samples of what can be done using machine learning and deep learning. And first, this is an implementation. By the way, I'm including URLs for you to check it out later. This is an implementation on Inbox by Google. And now this is available also in Gmail since maybe a couple of months ago. The idea behind this implementation is that it will suggest some replies. It's different than the suggestion that we get from the keyboard because those are using Markov chains. That means that it only simplifying it only groups together the words that we use often. In this case, this automatic replies learns how we answer emails or whatever the data they use to train it, and then make available for us some like pre-made answers built on whatever we usually do write to reply these emails. It's funny because the neural networks learn in a similar way as people learn. It's not exactly the same. We will dive a little bit into this in a couple of slides, but when they were training this, for some reason, like the default answer was, "I love you." And as sweet as this sounds, it's not exactly what we will want in our suggestion to reply our emails. It was like if the neural network didn't know what to do, like the fallback was "I love you." And similar to that, when we're having a conversation and we don't know exactly what to say, usually we have like a phrase or a word that we could use, and it's different from language to language. So there are several things that are similar on how humans learn. This is another sample on the music recommendation system. This uses a generalization and also deep learning. Humans do this a lot. I mean, when we're learning how things work in the world around us, we generalize a lot. So let's say, I don't know, I see a hummingbird and it flies. Then I see a pigeon and it flies. So I can generalize that every animal that comes with wings, it will fly. And then afterwards, I will learn that there are some exceptions, like penguins. So something similar is applied here for the recommendation system, mixing both deep and wide approach. This might be one of the famous results of deep learning. Last year, AlphaGo defeated the Go champion. This year, defeated the best player. I don't know why the best player is not the champion, but regardless of that, it showed that this artificial intelligence built by Google, it's improving. This is one of the projects of that applies reinforcement learning. We're going to see in a bit 3 types of machine learning, but this particular one, for me, it's the most interesting because it learns pretty much like people do. I really like learning by doing. I really like messing up while learning. It sounds kind of rough, but I think we learn a lot from our errors. And reinforcement learning is similar to that. So that's how this artificial intelligence learn how to play. You might remember Deep Blue from maybe 20 years ago, that it was an artificial intelligence built by IBM. At that point in history, they were using a lot of brute force. And how machine learning is working nowadays, it's a big shift, and that's how we get all this interesting technology around us. A few more samples. If you are into self-driving cars, this is a simulation that you can adjust in your browser and change some hyperparameters to see how this works. The goal is for the red car on the bottom to go as fast as it can, and also, over here it's like the speed, and also to pass other cars. So we can configure this, train the neural network, and see the result in the browser. So it's really fun to play with. This is another sample. It's called transfer style. Using a neural network, we can grab both the content and the style of a picture. In this case, we're grabbing the style of this picture and the content of this, and then mixing it up. Using something similar is how different kind of AIs have been able to paint, to write, and it's not exactly a work of creativity, but instead of that, it's learning how others have worked this previously and then building something new. And again, that's similar on how people work and how we learn. This is another example of reinforcement learning. In this case, it's playing Flappy Bird. Reinforcement learning works with a combination of punishment and reward. Remember, all this is math, but there's a mathematical function for either the punishment or the reward. In this case, the reward is going between the pipes, and that's how they build several AI agents for playing games. including AlphaGo, Flappy Bird. There's a paper from Google where they built AI agents to play several Atari classic games. Okay, there are a lot of more samples, but I found those interesting. And when I was doing my research for this talk, I also found interesting that one of the fathers of AI, John McCarthy, mentioned this quote: "As soon as it works, no one calls it AI anymore." And I want to mention this because everyone is talking about AI. Everyone is saying, I'm doing this, I'm doing that. And in several cases, it's only a lot of chained if statements. And it surprised me that at some point in history, several things like automatic garbage collection were called AI. Nowadays, that's called an algorithm, but we've been interested in AI for a while, and mostly because the tools were not available, a lot of things were called AI. So it's important to keep in mind that although my goal is to demystify the topic and stop seeing this as black magic or some black box, we're not trying to call everything AI. I took this from Twitter. It says, by today's definition, y equal mx plus b. That's the equation for a line. It's an artificial intelligence bot that can tell you where a line is going. This is a linear progression. Our basic approach to machine learning is a linear regression. But as I mentioned before, mostly on the startup scene, a lot of people are saying, we're doing machine learning, and there are only a lot of chain if statements, so keep that in mind. We're going to see several approaches to machine learning and how we can implement this on our projects. Okay, so can machines learn? In a sense, machines can learn, but it's not as people learn. Mostly because although there have been years and years of research, we're still not completely clear on how people learn. There are several approaches. There are several different works on this, like the multiple intelligence, and that some people learn in this way or another. But still, we are not crystal clear on how humans learn. So we can mimic some of this, but it's not going to be exactly as people learn. So what's machine learning, what's deep learning, and what's AI? The way I see it, AI is like an umbrella, like something that covers our idea of getting a machine to do something that's supposed to be only for humans. There are different approaches for this. One of those is machine learning. Machine learning is giving data to a computer and allowing it to figure it out how it will behave in the future. And that's a pretty long name. So instead of that, we use machine learning. So we're not saying machine giving data to a computer and figuring out how it will behave in the future. Instead of that, we use ML. And one of the tools for doing this is neural networks. And a network comes with different layers. When there are a lot of layers, we call this deep learning. Okay, so can machines learn? Yes, kind of. But we need lots of data and lots of processing power. That's why there's not a surprise that the companies that are doing this and offering APIs, like the ones we're going to review today, are the companies that already have our data, like Google, IBM, Facebook, Amazon, Microsoft. And that's why also it's not a surprise to see companies with a lot of processing power in the scene, like NVIDIA, because a GPU is really useful when training a neural network. For the sample that I'm going to show at the very end of this talk, I retrained a pre-trained existing model. So it was just giving new data using the same structure. and it took several hours on my CPU. A couple of days ago, I was reading about implementing a new project using something that's called show and tell that mixes two different approaches. One for identifying what's in a picture, and another one to say it in a human way. Instead of like saying, here's a person and there's a 90% chance of that, I would say, I see a person. And in order to do that, there's like already a TensorFlow cookbook to implement that. But in order to train the model, the README suggested around maybe 3 or 4 weeks of training using an NVIDIA Tesla. And they strongly suggest to do not use a CPU. So keep that in mind. We really do need lots and lots of data. I would say many million of entries. And also, we do need lots of processing power. So using a CPU, it's a good idea to try it out, but it might be a terrible idea if we're doing this in something more bigger, something aiming for production. So let's explain machine learning with a taco. I used to be someone who, when I went to a restaurant, as I mentioned, I'm from Guatemala. When I was at the university, there were not many options. So almost every week, me and my friends ended up at TGI Fridays, and I always order chicken fingers. For some reason, I reviewed the whole menu and always ended up ordering the same. Eventually, I come to a moment in my life where from which I've been trying to feel comfortable not having the control of everything and trying new things. And luckily for me, this moment was near a moment where I've been traveling a lot for conference. So I've been enjoying traveling, and also I've been enjoying having some new food. One of my favorite kind of food is Mexican food. I really like tacos. And we're going to use this analogy to explain and to approach to the topic. So, should I have Mexican food? As I mentioned before, it's one of my favorites kind of food. But when I'm deciding what to eat, when I'm reviewing the menu, or deciding which kind of restaurant should I go, there are many questions that I should answer. Like, am I hungry? Am I alone with friends or in a date? How much would I like to spend? And with all these questions, we can build a tree. This is called a decision tree. So the first node might be, am I hungry? If I'm not hungry, then no Mexican food for me. Okay, I'm hungry. Am I alone? If I'm in a date, getting street tacos might not be the best idea. So if I'm alone, I have like more power of decision. So yeah, I do want tacos. And how much do I want to spend? With decision tree, we have classification. In this case, we're deciding, should I get the tacos or not? This is one of the simplest approach to machine learning. But it's not the only one. What if I would like to know how much does a taco cost? And the same applies with other kind of food. It's interesting because I'm privileged enough to get the chance to travel several parts of the world. And usually I like to ask like the average price of different things to compare it to other places. So tacos are really cheap in some places. I've had some really good tacos in Mexico City, paying like maybe 50 cents or $1. And also I have great tacos in San Francisco, paying like maybe $8, $9 per taco. So it's a huge difference. So the price of the taco will depend on several variables, like the city or the country. To make things easier, like keep it locally. It also depends on the neighborhood. The type of eatery might be in a restaurant or maybe a food truck, and also the ingredients. With all this, I can predict what will be the price of a taco. These variables are not equally important. Neighborhood might be more important, or maybe the type of eatery, or maybe the ingredients, but they are not equally the same. Using these variables, I can predict what will be the price of the taco. But also, I need information. In order to do that, we can build a multivariate linear regression. And this is another approach, basic approach, into machine learning. And usually when I'm speaking about this, someone approaches me and says, hey, I learned that at the university. It's called statistics. Yeah, it's true. There are a lot of statistics, linear algebra, calculus, in order to build something with machine learning. So these two are called supervised learning. One is classification, the other one is regression. There are many other ways to approach to this problem, but the important thing that I would like for everyone to understand here is that that's one of the basics approach to machine learning, first, and also that's called supervised learning. In this case, we are labeling the data because we already have labels. It might be the case that we don't have labels at all, but we have the data. Like, we have the neighborhood, type of eatery, and ingredients, but we don't have the final price of the taco. In that case, that's called unsupervised learning because we don't have the labels. And the question that we can answer is a bit different. Instead of what's the price of the taco, we can answer which tacos are the best for me. So we can build a system for recommendations because without labels, instead of predicting how it's going to behave in the future, the price of the taco, we can build a cluster and also detect some anomalies, identify outliers. These two have been around for a while, supervised and unsupervised learning. And the other one that I mentioned is reinforcement learning. Continue with the taco analogy. I might have taken this too far. We can answer the question, how should I eat a taco? Should I use silverware? Should I use only my hands? Apologies, I only found this in Spanish, but to eat a taco, you should tilt your head in a 45 angle degree, hold your arm in a 90 degree angle, keep the plate just beneath your hand, and then grab all the tacos. Also, I could answer, how many tacos should I eat? Because here we talk about a delayed reward. In the previous cases, it's immediate. Like, if I'm predicting the price, I'm saying like, based on the ingredients and the type of eatery, I can predict that the price is going to be this one. Or if I'm doing some cluster analysis, I can group different kind of elements, like tacos in this case, but it's immediate. With reinforcement learning, I could ask something like, how many tacos should I eat? Because if for some reason, I have only one, at the moment, it might be, I might feel fine, but eventually, I will be hungry. But if I have too many tacos, eventually, I'm going to feel sick to my stomach. So that's why it's a delayed reward, because at some point in the future, I'm going to get an announcement saying, yes, this is fine, or no, for some reason you messed up, but it's not immediately. And that makes things interesting. And that's how the AI gaming agents are built. So, no more tacos. We're going to speak a little bit about houses. It's exactly the same. Bedrooms, square feet, and neighborhood instead of type of eatery and ingredients for the tacos. And I grabbed this sample from an article that's called Machine Learning is Fun. Might be difficult to see, but here's the URL. It's 8 or 9 part article in Medium. Be sure to check it out later. It's really good, and it's explained in a way it's easy to grasp and understand what all these concepts are about. So this is our data. In order to build a linear regression, we're predicting what's going to be the value in the future. So we grab a part of the data to train and another part to validate if the training was OK. So we have weights. This is how important is a variable in our equation. Using these weights, we do a multiplication for bedrooms, square feet, and neighborhood, our variables, and afterwards check how far away are we in our prediction from the actual data that we have. So we calculate an error. And in order to improve this model, we're going to iterate until that error is a minimum. We have a little bit of math jargon here. It's multiplied by a fraction, mostly because we're going to use calculus. And if you remember from, I think that's high school, when we do a derivative, a partial derivative, we use this as a constant. So using this constant that's already here, we're going to eliminate that, and it's going to be easier for doing all the math. Eventually, we're going to try new values to minimize errors. These weights are going to be random at first, mostly because we want to start at different places and not get stuck at some local minimum. Instead of that, we're aiming to a global minimum. In order to look for this minimum and to minimize this function, we're using something that's called gradient descent. And if we graphic our variables, it might look like this. We start at some point around here and then move aiming for the minimum. Eventually, we're going to be really close and have a way to predict what's going to be the value of the tacos or the houses or whatever we're doing. At some point, we can make a chart for that. Let's say that we have our 3 variables, and each one comes with a weight. Eventually, that gets us a price estimate. If for some reason our model doesn't work for all the data, let's say that for medium houses, this doesn't work, then we will need to build a new model for that. If we need more than one model, each one will come with a set of weights, a different set of weights, and eventually we will need a way to integrate all this. Something similar to this chart, when we have our different price estimates, each one with its own weight to give a grand total of the price estimation. If we put together all these different models, we get something similar to this. And that's a really simple neural network. It works loosely, and it's loosely based on how neurons work, but more than mimic the exact behavior, the important thing here is that we have an input, an output, and some mathematical function that activates all this. There are several functions, math functions, to approach to solving this problem, but the basic one would be the step function, that there's a threshold, and it will give 0 if it's under that threshold, and otherwise it will give 1 as a result. So that's called, what I just mentioned, it's called a perceptron. But there are a lot of many different approaches to build neural networks. Again, it's difficult to read, but here's the URL. This is just like 1/3 or maybe half of the chart. And each neural network have a a different problem that it will solve. For example, I don't see it, but it might be somewhere. The CNNs, convolutional neural networks, are especially designed to solve computer vision problems. There are another approaches like recurrent neural networks or long short-term memory neural networks. That's one case of this that are useful for NLP. And eventually, we'll find that there are several tools available to solve the problem that we are facing. Okay, so that's enough with the theory. No more tacos, I promise. And now I would like to review a few APIs so we can start right away working with machine learning. I think it's important to understand that there are several things happening like under the hood, but if we want to do this right away, there are also APIs that are already available and built for us to use. So the way I see it, there are three different paths to approach to this. The first one is use a previously built API offered by Google, Microsoft, IBM, or any other company. It's easy, but it's not flexible. The next step would be retraining a model using some machine learning framework like TensorFlow, Keras, Theano, Caffe, etc. And the final one will be build our own model using our own data. As we get close to this third step, it's more complex, but also it's more flexible. So we're going to cover the first one with three different APIs. Google Cloud Vision API, Cognitive Services for Microsoft, and IBM Watson. We'll also see a sample using Mobile Vision API that's offline, that's running on the device. And finally, we'll see a sample retraining a pre-existing model using TensorFlow. The idea here is to see the result, and there are several snippets of code, and the code is not that difficult. And what I'm aiming to do with this is for everyone to see that this is not something too difficult to approach. Even though there are many math things happening, and there are already neural networks working and trained and doing inference, for us to use an API, it's not going to be different from using an API from any other thing. So basically, we need to grab a key, see if there's already an SDK, and if not, do the REST calls by ourselves. If there's an API, it's going to be easier because we only call these methods. So the sample that I'm going to show, it's taking a picture, either from the gallery or the camera, and then identifying what's on the picture. Also, we're going to take faces and identify where's the face located on the image and if the person is smiling or not. So it looks like this. It's a pretty simple layout. And working, it will look something like this. Then I'm grabbing a picture. I'm going to read this because it might be too small. It's a river, water, tree, body of water, lake, and many other labels. Remember, you can check it out later to see like the result. All this code is on my GitHub. It's still in Java. I'm working on migrating this to Kotlin. I didn't feel comfortable enough to publish it right away, but maybe in a couple of weeks, it will be available also in Kotlin. As I mentioned, if I take a picture, it will identify that there's a person there and also the smile. Because if I take a different picture where I'm not smiling, then it will only do this rectangle around the face. OK, so Cloud Vision API. It will identify faces, labels, logos. It comes with a safe search. Although it identifies faces, it will not do face recognition. With this, what I'm trying to say is that it will not say, hey, this is Adrian. It will say, hey, here's a person, and that's it. Also, it identifies some landmarks, and it recognizes text. In order to work with Cloud Vision, we need to build an image request, add the image to that request using a base64 encoding, say to that request which features are we trying to get. In this case, I'm aiming for label detection and face detection. And then use a vision builder and execute the request. So basically, it's a three-step process: adding the image, saying what I'm looking for in the image, and executing the request. Eventually, when I get the result, this is all JSON-based, so I'm going to need to parse the result. Then I can grab the labels and the scores. The scores are a probability, so it's a value between 0 and 1 that says how probable is that whatever the API identifies is going to be there. In this case, we have the first label is body of water, no, river. River, and it's 0.899. So it's almost 90% sure that's some river in the picture. In order to do the rectangle around the face, I'll grab this position from the result and something similar for the smile. In the case of the smile, I'm also conditioned that's a likelihood of joy and grabbing the position of the lips and the mouth. With Microsoft Cognitive Services, we can do something similar. In this case, it will also identify the age of the person. It also comes with a safe search, so it will give us a score if the content is adult content. And also, it will give several tags and description. In code, this means that I'm going to specify the features. Keep in mind that's a little bit different from the previous case. I need to specify also the image, and then execute the request. It's the same process, a little bit more short maybe because of the SDK, but that's it. Here I'm taking a picture of a bottle. So it says a bottle of alcohol sitting on a table. It's giving me the caption right away. And it's 70% sure that that's a bottle of alcohol sitting on the table. It also gives me the tags. It says table, 97%, indoor. The tags are table, indoor, bottle, etc. Something similar with the face, but in this case we have age and gender. And let's see how it goes. And it says 42. It's not going easy on me. And it's 100% sure that there's a person and also ceiling, indoor, wall, man. It identified correctly my gender and not exactly my age. And there's also IBM Watson. IBM allows to train on the cloud. The thing that we're going to do with TensorFlow in a couple of more slides, Watson allows us to do that on the cloud, and it's easier if we don't want to install everything on a local computer. Also, search for similarities, like cognitive services, although neither of those give you like recognition of or tagging of an image, saying this is that person. It can group on similarities, something that Cloud Vision would not allow. So again, we build the classifier. In this case, we're trying to get faces and classification. And with something similar to the previous case, we will get different results, like bottled water, drinking water, water, food, mineral water. So with the previous case with cognitive services, we got a caption. In this case, we're getting only the words. It depends on the API, but we have several similar features. Also, we can identify the age. Let's see if I get better luck with this API. Counter table, etc. So it says I'm 55 or 64. But at the very end, it also identifies if I look alike to someone famous. In this case, I look alike in a really high percent. Let's say it's 0.95. So I'm similar 95% to Nahid Nenshi. I never heard of him before, so I went to Google Images, Google Nahid Nenshi, and it turns out it's a politician. It's the former mayor from Calgary. I might have a career in politics that I'm not aware of. So yeah, that's Watson. There are many other APIs like Haven on Demand. This comes with a license plate recognition. Also, Amazon. And with this, there are many, many more. What I was trying to do here is showing that it's approachable. You don't need to know a lot more than something that you already know, how to use an API, how to parse some JSON, and we can start to work with a machine learning right away. All these are cloud-based. So mobile vision is based on the device. It's basically the same, a little bit more constrained, but basically the same. And for mobile vision, I decided to work on something similar to the filters of Snapchat and Messenger. And nowadays, it seems like every instant messaging app comes with a way of adding filters. So instead of a puppy face or rainbows or picking rainbows, I chose to draw a Galileo face over the person that's detected. I work at a university in Guatemala that's called Galileo. That's why I chose that. And we need to build a face tracker. And with that face tracker, we can add an overlay. If you already have worked with a surface view, this is quite similar. The overlay is a custom view. The only thing new is the face tracker. There's a really nice sample available in the official samples of Google, including googly eyes, physics, and everything. For me, that was way too complicated. That's why I decided to build this sample that's more easy, just a simple overlay. So in this case, on the onDraw method, we are checking if we are drawing or not. And in case we're drawing, we're scaling the bitmap. That's because if the camera is really close to the face, we need the bitmap to be bigger. And if it's far away, the bitmap will be smaller. And it looks something like this. Notice that when I am close to the camera, the image is bigger. And if I cover my eyes, the image disappears, mostly because it's not detecting a face anymore. And this is the code that's making all of that. We have a face detector, detecting all the landmarks in fast mode. And I'm setting just a minimum value for the face. With that detector and the tracker in the previous slide and the custom view, we have a Snapchat-like filter setup. This is where I configure the camera source. As I mentioned, I'm using a surface view in order to make it similar to any other application using the camera and giving the feedback in the phone screen. So finally, TensorFlow. This is an open source machine learning platform. Some people call it a framework. It's fast, flexible, might be the trendiest or the most used at the moment from all the frameworks. As I mentioned, there are neural networks with inputs and outputs. When we have a lot of layers, these are called hidden layers. It's called deep learning. How deep? Couple of hundred, maybe. If there are not a lot of hidden layers, it's called a shallow neural network. TensorFlow looks like this. You work with Python and can, after we give all what we need, it will generate a graph. There are many ways to approach building a neural network. We can do it on pure Python. By the way, I suggest using Python because there are a lot of different libraries. We can use, we can build our neural network using NumPy. And we can use TensorFlow. With a couple of lines, it's possible to build a full neural network using backpropagation. That means there's a feedback to correct the error and a better approach to finding a way to predict the behavior that we want. If we are starting with TensorFlow and we would like to know what means having more neurons or a different number of layers, there's a playground on the browser where we can configure the learning rate, the activation function. As I mentioned, the perceptron uses the step function. There are many other similar math functions where we can configure here, see the output on a visualized way. It's quite useful when we're starting. And in this sample, I'm taking Inception 2. That's one of the best available models for computer vision, for labeling the images and retraining it. So we're going to retrain it using Docker to grab the image of TensorFlow. Then it already comes with a retrain script. We only need to specify the images. For this sample, I took from Google Images two different things: images from Alice in Wonderland as a cartoon, and images from Stitch from Disney. And using the same structure that's already available in Inception, with this, we are retraining the same model to identify those two. If you watch Silicon Valley HBO show, at some point, there's like the idea of someone is an app called Not Hot Dog. And it can only identify if something is a hot dog or not. Something similar happens in this case, because although Inception is trained to identify a lot of things, with this retrain script, I'm only given two things: either Alice in Wonderland or Stitch. So we need Bazel to build it. And then we need to optimize for inference. Keep in mind that although the phones are quite powerful, we need lots and lots of resources. And finally, we have an executable to try it out. For this, I'm using the sample from TensorFlow, only changing the name of the nodes and the values of the standard deviation and the mean. And let's see it working. So here we have the test with an image. I'm going to pause the video for a minute. And it's 90% sure that's all Alice, and only 9% that's Stitch. And when we open the image, it's in fact Alice. I can try the same using my phone, so I'm about to do that. And using Visor, notice that because I'm using the phone, taking a picture of the screen, the values are going to be different. And here, let me try a zoom. It's 57.9%, the same image. And also, the same happens with a Stitch. Let me pause this for a second. And here we have Stitch, 92%. And using the phone, it's, in this case, 78%. And that's using TensorFlow. So the samples are available on my GitHub. We've seen several ways to approach machine learning, learn a bit of theory about machine learning, and hopefully everyone in the room sees machine learning as something approachable. It's an interesting subject, an interesting topic, and from my point of view, in maybe 1 or 3 years, we'll be doing this a lot. So instead of saying I'm doing mobile or I'm doing web, we'll be saying I'm doing machine learning with mobile or web. Instead of being the end, mobile will be the mean to achieve something else. If at some point you want to get scared that robots are going to take over, feel free to check out Boston Dynamics. It's amazing. They even have a TED Talk where one of their robots give a live demo. But keep in mind that a lot of time ago, one of the fathers of AI said in 1956, in 20 years, machines will be capable of doing everything humans do. And 20 years later, when it didn't happen, he said it again. In 20 years, in the 90s, he chose not to say that anymore. So this is the ARPA challenge. Robots trying to do really simple tasks and failing miserably at it. I'm not afraid of machines taking over. I'm not afraid of Skynet, because machines learn from us. And not many people want to destroy everyone and attack with lasers. What most of people have, it's different types of bias. So it's important to keep that in mind, because machines will learn from us. So if we have bias, our machine learning algorithm will have this bias. So instead of being afraid of Skynet or something similar, I think it's important to democratize AI, make a way for more people to have access to different kind of tools in AI, and take our bias and put it to the side in order for us as a group, as humans, to generate data that will be useful for machines to learn. That's the URL for the slides. And as I'm the only thing standing between you and the launch, this is my final slide. So thank you very much. I will be around today and tomorrow for any questions.